The birth of the universe is one of the most profound and awe-inspiring topics in modern science. To truly grasp its significance, we must first imagine a time before anything existed. This means stepping into an era where there was no matter, no energy, and not even space or time. It's a realm beyond our everyday experiences, but it forms the foundation upon which our understanding of the cosmos is built. In the beginning, the universe was a singularity, a point of infinite density and temperature. This singularity marks a boundary for our current scientific understanding. Beyond this point, conventional physics breaks down, and our usual concepts of space and time cease to exist. It is here, in this mysterious and unfathomable state, that the story of the universe's birth begins. The mystery surrounding the birth of the universe is not just confined to physicists and cosmologists, but captivates anyone with a sense of wonder about the cosmos. These first moments are shrouded in both excitement and uncertainty. The universe we see today, with its countless galaxies, stars, and planets, all emerged from an incredibly hot and dense state. But how did it all begin? This question drives much of the research and curiosity in modern cosmology. One of the most exciting aspects of studying the universe's birth is the potential to uncover new physics. The conditions of the early universe are so extreme that they provide a natural laboratory for testing the limits of our current theories. For instance, the Big Bang theory, which describes the universe's expansion from a hot, dense state, is well supported by observational evidence. However, it leaves many questions unanswered, particularly about the very first moments. The excitement also comes from the innovative ideas and hypotheses that scientists propose to solve these mysteries. Concepts such as vacuum fluctuations, quantum foam, and multiverse theories offer tantalizing glimpses into what might lie beyond our current understanding. These ideas are not just abstract theories, but are grounded in mathematical rigor and experimental investigation, pushing the boundaries of what we know. Moreover, the quest to understand the universe's birth is a journey that connects us to the broader narrative of existence. It is a reminder that we are part of a vast, dynamic cosmos that has evolved over billions of years. This profound connection to the universe's origin stirs a deep sense of belonging and curiosity, urging us to continue exploring and questioning. In conclusion, the mysteries and excitement surrounding the birth of the universe are a testament to human curiosity and our desire to understand the cosmos. What do we mean by nothing? Usually, it means an empty space, like an empty jar or a vacant room. This is our common, everyday idea. It implies the absence of objects, sounds, or light. But is this truly nothing in a cosmic sense? Even an empty room still contains air molecules. It exists within space and is governed by physical laws. Cosmology challenges us to think much deeper about this concept. It pushes us beyond these simple notions of emptiness. Our everyday intuition about nothingness is quite limited. We might imagine removing all matter and all energy. But what about the very fabric of space itself? And what about the flow of time? Can nothing truly exist if there is no space to be empty in? Can a state of nothingness persist without time passing? These are incredibly difficult questions for the human mind. Our minds struggle to fully grasp such an abstract state, a true void, devoid of even dimensions or a place to be. This is where the cosmological definition of nothing begins to take shape. Philosophers throughout history have long debated the nature of nothing. Is it an absolute void, a pure and utter emptiness? Or could nothing actually be a state possessing hidden potential, a state from which something remarkable might eventually emerge? This fascinating idea is certainly not new. Ancient thinkers pondered the concept of creatio ex nihilo. This Latin phrase translates to creation out of nothing. The question of what nothing truly is remains a profound one. It forms a crucial bridge between philosophical inquiry and scientific investigation, especially especially when we consider the mysterious origin of our entire universe. For cosmologists, nothing is far more than just a philosophical puzzle. It becomes a specific technical concept within their field. It is not the simple absence of things we usually imagine. It might describe a primordial state that existed before our universe, a state where our current known laws of physics perhaps did not apply, or alternatively, a state that was governed by its own unique set of rules. This pre-cosmic nothing could be the ultimate precursor to everything. Understanding this specialized and nuanced meaning is absolutely crucial. It is the key to unlocking and exploring the universe's very first moments. Modern physics offers a surprising perspective on nothing. In quantum mechanics, empty space is not truly empty. This baseline state is called the quantum vacuum. It is dynamic and energetic, teeming with potential activity. Particles can blink into existence and annihilate. This redefines nothing in an exciting way. The quantum vacuum is the lowest energy state, but it is not zero energy due to vacuum fluctuations. These are tiny ripples in the fabric of reality. This dynamic nothing is vital for science. It helps explain how the universe might have begun. A quantum fluctuation could grow into our universe. This concept is key to modern cosmological theories. It offers a pathway from nothing to something. The cosmic nothing is active and fertile, governed by the laws of quantum mechanics. Understanding this is essential for exploring cosmic creation. It helps us appreciate the mystery of our universe's birth. Our journey into the universe's earliest moments now brings us to a profound challenge. This challenge is not just about complex equations or elusive particles. It is about the very limits of human understanding itself. We must consider a state before the existence of time and space as we know them. Our entire conscious experience is woven into the fabric of these two fundamental concepts. We perceive the world around us in three spatial dimensions. We experience life as a sequence of events unfolding in time. Trying to imagine their absence is a monumental task for our minds. The language we use every day is deeply rooted in space and time. Think about common words: before, after, here, there, above, below. All these terms presuppose a spatial or temporal context. How can we accurately describe a realm where such concepts might not apply? It is like trying to explain color to someone born without sight. Our linguistic tools, so effective for navigating our familiar world, falter at this cosmic boundary. We search for words to describe the indescribable, stretching our vocabulary to its breaking point. This makes discussing such topics incredibly difficult and prone to misunderstanding. Human brains have evolved over millennia to understand a world governed by cause and effect. We are wired to perceive events happening in a specific order, in specific locations. This linear progression of moments, this spatial arrangement of objects, is fundamental to our survival and comprehension. To contemplate a state where there is no sequence and no place is deeply counterintuitive. It feels alien, almost impossible to truly grasp. Our minds naturally seek patterns and frameworks, but here, the familiar frameworks dissolve. This creates a sense of cognitive dissonance, a feeling of peering into an abyss of the unknown. Therefore, when we try to understand the universe before time and space, we hit a wall of intuition. Our everyday experiences, our evolved mental shortcuts, become obstacles rather than aids. We must acknowledge this inherent limitation in our human perspective. This intellectual humility is crucial as we venture into these abstract domains of cosmology. It requires us to rely less on what feels right and more on the rigorous, often abstract tools of science and mathematics. It is a call to think beyond our ingrained perceptions. How do scientists and philosophers think about a state devoid of time and space? The answer lies in abstraction and theoretical tools. Mathematics transcends human sensory experience. Equations describe relationships we can't visualize. Theoretical physics builds models of the universe's earliest conditions. Scientists use analogies to bridge conceptual gaps. Phrases like "space shrunk to a point" help our imagination, but analogies are limited and can be misleading. They use space and time to describe their absence. They are like guideposts in a dense fog. True progress requires moving beyond mental images. Some ideas explore existence without space and time. Perhaps pure information or fundamental laws existed. Could the universe's blueprint exist in an abstract realm? This is highly speculative territory. It pushes us to question existence detached from the physical. Do laws of nature depend on space-time or transcend it? Contemplating pre-space-time reality confronts profound questions. Our consciousness is intertwined with time and space. Removing these pillars challenges our cognitive biases. Can we understand a state alien to our being, or are we projecting human thinking onto the unknown? This intersection of physics and philosophy marks a frontier of human thought. Theoretical physics offers potential pathways beyond our everyday intuition. Physicists use theories like string theory and loop quantum gravity to explore realms where classical understanding breaks down. These frameworks attempt to describe reality's fundamental building blocks. Space and time might be composed of tiny, discrete units. This challenges our standard ideas of causality and the universe's beginning. We are on the cutting edge of scientific inquiry, exploring profound questions about our cosmic origins. Our exploration now leads us into the bizarre realm of quantum mechanics. Classical physics imagines a vacuum as a perfect void, but quantum theory reveals a dynamic reality. The quantum vacuum is not truly empty. It represents the lowest possible energy state. This minimum energy level is not zero, giving rise to vacuum fluctuations. These fluctuations are a consequence of the Heisenberg uncertainty principle. Tiny amounts of energy can briefly appear, manifesting as pairs of virtual particles. This energy, known as zero-point energy, has measurable effects like the Casimir effect. The quantum vacuum is a dynamic stage, alive with fleeting bursts of energy and transient particles. Building upon the idea of an active vacuum, we encounter quantum foam. Physicist John Wheeler proposed that at the Planck length, spacetime resembles a chaotic foam. At these scales, quantum fluctuations warp and distort spacetime. Instead of a smooth fabric, spacetime becomes a seething maelstrom. Tiny, fleeting wormholes and microscopic black holes might constantly pop in and out of existence. This dynamic landscape contrasts with the orderly spacetime of general relativity. Quantum foam suggests spacetime might be an emergent property, like water's smoothness from H2O molecules. Understanding quantum foam is crucial for theories describing the universe's first moments. How could a quantum vacuum and chaotic foam explain our universe's birth? One idea is that our universe originated from a grand vacuum fluctuation. This fluctuation, linked to cosmic inflation, could have expanded rapidly, smoothing out irregularities. A key question is where the energy came from. One proposal is that the universe's total energy is zero, with positive energy balanced by negative gravitational energy. These concepts are at the frontier of theoretical physics, supported by elegant mathematics. Scientists are developing theories like string theory to shed light on these earliest moments. Exploring vacuum fluctuations and quantum foam provides a framework for understanding our universe's emergence. What if our universe is not the only one? This is the core concept of the multiverse. It suggests our cosmos is part of a larger collection of universes. This idea emerges from advanced theories in physics, addressing the fine-tuning problem. A multiverse offers an explanation. Countless universes with different constants making our existence possible. Theories like cosmic inflation and string theory point towards a multiverse. The implications are profound, shifting our cosmic perspective. Our universe would be one member of an unimaginably vast ensemble. This realization expands the definition of existence. The theory of cosmic inflation might lead to eternal inflation. This idea suggests inflation continues in distant regions, creating new cosmic domains. Within this inflating background, new universes can be born. These bubble universes form from patches that stop inflating and evolve slowly. Our universe is one such bubble in an ever-growing foam of universes. Eternal inflation implies a multiverse with no definitive beginning or end. Each Big Bang marks the birth of a new bubble universe. This concept suggests a perpetual cycle of creation, altering our understanding of cosmic origins. Multiverse theories are highly speculative, lacking direct proof. Other universes are causally disconnected, making them difficult to verify. Scientists approach these concepts with excitement and caution. The core principle of falsifiability poses a hurdle for many multiverse proposals. Indirect evidence might eventually support these ideas. The concept of a multiverse carries profound philosophical implications. It reshapes our understanding of our significance within a vast cosmic landscape. The ongoing debate stimulates critical thinking and innovative approaches to understanding our cosmos. As we reflect on the birth of the universe, it's essential to appreciate the breadth and depth of the journey we've undertaken. We've delved into the concept of nothing, which in cosmology is a far cry from our everyday understanding. Nothing can be teeming with activity in the form of vacuum fluctuations and quantum foam, challenging our perceptions and pushing the boundaries of what we consider possible. This seemingly paradoxical notion that nothing can give rise to something forms a cornerstone of modern cosmological theories, offering profound insights into the nature of existence. We have also examined the limits of human understanding before the existence of time and space. Our cognitive frameworks, deeply rooted in the notions of temporality and spatial dimensions, struggle to comprehend a state where these concepts do not apply. Theoretical physics provides abstract tools and models that extend beyond these limitations, suggesting that space and time themselves might emerge from more fundamental pre-geometric conditions. This intellectual endeavor showcases the remarkable adaptability and creativity of the human mind in seeking to understand the cosmos. Further, our exploration into theoretical physics has revealed the intricate dance of particles and energy within the quantum vacuum. The interplay of vacuum fluctuations and quantum foam illustrates a universe that is fundamentally dynamic even at its most empty. This understanding supports the idea that the universe could have sprung from a quantum fluctuation, a concept that dovetails seamlessly with the theory of cosmic inflation. Inflationary theory, in turn, offers a compelling narrative for the universe's rapid expansion, smoothing out irregularities and setting the stage for the cosmos as we observe it today. Finally, we ventured into the speculative but intriguing realm of multiverse theories and timeless existence. These ideas propose that our universe might be one of many, each with its own distinct properties and physical laws. Eternal inflation, in particular, suggests a never-ending creation of new universes within an inflating cosmic landscape. This broader context challenges our understanding of the universe's beginning, shifting the focus from a singular event to a perpetual process of cosmic genesis. Such theories, while speculative, push the boundaries of our knowledge and inspire new lines of inquiry. Reflecting on the universe's birth, we recognize this quest is more than academic. It's part of our human identity. Our desire to understand the cosmos speaks to a deeper yearning to know our place in the universe. Exploring the earliest moments of existence unravels mysteries that have fascinated humanity for millennia. This journey connects us to the broader narrative of the cosmos, highlighting our profound interconnectedness. The quest for knowledge in cosmology is a testament to human curiosity and scientific inquiry. Each discovery adds a piece to the vast puzzle of our understanding. The universe's birth is not just a scientific inquiry, but a deeply human endeavor, enriching our understanding of reality. This quest will continue to inspire and challenge future generations. Let us journey back to the very first moment, the dawn of everything. Scientists call this the Big Bang, but it wasn't an explosion in space. Space itself began then. It was an expansion, a universe rushing into existence from a point of unimaginable energy. This event marked the start, the birth of reality itself. Before the Big Bang, there was no before as we understand it. No space, no time. Everything we see, everything we are, started in this single, monumental event. All the stars, galaxies, planets, and every speck of dust, every bit of energy, was contained in that beginning. Then it began to expand, and it continues to expand today. This is the legacy of the Big Bang, a universe still unfurling. When we talk about the Big Bang, we're talking about the ultimate origin story. It's a story pieced together from evidence, from the light of distant galaxies and the faint afterglow of that first fire. It's the story of how everything came to be. A story that starts with a bang, a truly big one, the one that made us all. The universe's expansion is still happening, carrying galaxies farther apart. Our scientific creation story is written in the stars and the cosmic background. The Big Bang is not just history, it's the reason we exist, and it all began in a single, extraordinary moment. Scientists often say T-demagux 0 seconds, the moment time began. It's not just a starting line, it's when our cosmic clock started ticking. Before this, there was no time, no seconds, no minutes, no years. Time is a dimension, like space, and it needed a beginning. The Big Bang was that beginning. So, T-0 is our reference point, the start of cosmic history. From this instant forward, we can measure and chart the universe's evolution. Our minds expect cause and effect, but with the universe, time itself is part of the story. Asking what happened before T-0 is like asking what's north of the North Pole. The question doesn't fit. T-0 isn't just a number, it's the birth of duration, the start of everything that followed. It's where our physics and our understanding of the universe truly begins. The first tick of the cosmic clock, the moment that set everything in motion. What was there before the Big Bang? Physics gives us a strange answer. There was no before. The Big Bang didn't just create matter and energy, it created space-time itself. If time began at T-0, then before loses its meaning. Imagine no space, no here or there, no up or down, no time, no past, present, or future, no matter, no energy, no light, no particles. This nothingness isn't like an empty room, it's a true absence of physical reality. It's a deep puzzle for scientists and philosophers alike. How can something arise from such nothing? Or was it a different kind of something entirely? The Big Bang challenges our intuition about beginnings. It forces us to rethink what nothing really means. The universe emerged from a state beyond our current understanding, and that's the mystery at the heart of it all. So, how did it all start? For a long time, the leading idea was the singularity. Imagine everything in the universe, stars, galaxies, all matter and energy, squeezed into an infinitely tiny point. This is the singularity, infinite density, zero volume. It sounds impossible, but that's what the math suggested. The entire observable universe, compressed smaller than an atom. This idea came from Einstein's general relativity. Run the clock backward, and everything converges to this single, unbelievable point. The T-0 moment, the singularity, was once the accepted starting point, but it's a paradox, infinite properties where physics breaks down. The singularity is a powerful concept, but also a sign that our story is incomplete. It's a cosmic question mark. Our minds struggle to grasp it, and our equations can't fully describe it. The singularity hints at deeper mysteries waiting to be solved. It's where our understanding meets its limits. The idea of a singularity, everything crushed into one tiny spot, is dramatic, but for scientists, it's a headache. Infinity in equations is a red flag. It means the theory is struggling. Physics prefers things that are measurable and finite. Infinite density and zero volume are not just philosophical puzzles, they're mathematical roadblocks. Our tools break down, giving us nonsensical answers. Most physicists today don't believe the universe truly began from a perfect singularity. It's more likely a sign that our theories are incomplete, missing crucial pieces for such extreme conditions. New ideas are emerging, challenging the classical picture. Perhaps the universe started at a very small, yet finite, size, not an infinitely small point. Quantum fuzziness might prevent a true singularity from forming. This is where the cutting edge of physics lies, trying to smooth out that problematic point. The quest is to find a more complete beginning. The singularity is a clue, not the final answer. To understand the Big Bang, we need to talk about Einstein and his general theory of relativity. Gravity, he showed, isn't a force, but a warping of space and time. Imagine a bowling ball on a trampoline. Mass bends the fabric, and objects follow those curves. Massive objects like planets and stars warp space-time, and that's gravity in action. General relativity predicts orbits, explains why light bends, and even predicted black holes. Crucially, it showed the universe can't be static. It must expand or contract. Observations confirmed it. The universe is expanding, galaxies rushing apart. Play the movie backward, and everything comes together, hotter, denser. This leads directly to the Big Bang idea. Relativity describes the cosmic expansion beautifully, but it hits a wall at T-0, at that initial, tiny point. That's where our current understanding stops, and where new physics must begin. Now, let's shrink down to the world of the very small, the realm of quantum mechanics. Quantum mechanics is the physics of the subatomic world, where reality is fuzzy and weird. Particles can be waves, and uncertainty rules. You can't know everything about a particle at once. Energy can appear and disappear for brief moments. Particles pop in and out of existence. It's a world of probabilities, not certainties. Quantum mechanics underpins much of modern technology and reveals a reality stranger than we imagined. So why bring it up? The universe's first moments were incredibly small and energetic, precisely where quantum effects dominate. Any complete description of the Big Bang must include quantum mechanics. The universe was once a quantum baby. Quantum mechanics is essential for understanding the very beginning. It's the key to the earliest moments of the cosmos. Without it, our story is incomplete. The Big Bang is where the quantum world and the cosmos meet. Here's where the story gets really exciting and challenging. We have two magnificent theories: Einstein's relativity for the big, quantum mechanics for the small. Each works perfectly in its own domain, but the Big Bang is where both must apply, unimaginably small and incredibly dense. The problem? They don't play nice. When combined, the equations break down, giving nonsensical answers. Relativity is smooth, quantum mechanics is lumpy. They speak different mathematical languages. This is one of science's biggest unsolved puzzles, the quest for a theory of everything, or quantum gravity, a single framework to unite relativity and quantum mechanics. Such a theory would unlock the secrets of the universe's birth. And perhaps black holes, too. It's the holy grail for physicists. So, where does that leave us? With the Big Bang, T-0 and the singularity. We know our universe had a beginning and has evolved over billions of years. We understand much about what happened after the start, but that first instant remains shrouded. The perfect singularity is likely an oversimplification, a sign our theories are incomplete. Physicists are exploring new ideas, string theory, loop quantum gravity, and more. These theories offer glimpses of what might have happened at the dawn of time. Perhaps the universe bounced from a previous state or began as a fuzzy quantum region. The truth is, we don't know for sure, not yet. Science is a journey, peeling back layers of cosmic mystery. The Big Bang Theory is a triumph, but the story is unfinished. There are still puzzles to solve, and the quest continues. We keep searching for the deepest understanding of where it all came from, and our place in the cosmos. We gaze at the stars above us. A profound question often arises. Where did all of this truly begin? This deep curiosity is ancient. It is a part of being human. We instinctively long to understand our origins, our unique place in the vast, sprawling cosmos. This is a fundamental driving quest for knowledge. It connects every one of us to the universe and its grand narrative. This vital quest is not just about Earth. It's not solely focused on our solar system, or even our home galaxy, the Milky Way. It encompasses absolutely everything we see, all of space, stretching out infinitely, all of time, from its start to its end, all matter and all forms of energy, the grand, breathtaking totality of existence. The universe in its complete, awesome entirety. We seek the very first chapter. Scientists now widely believe our universe had a start. There was a definite moment of cosmic creation. It wasn't simply always here, existing endlessly. There was a unique point before which, well, the concept of before becomes tricky. Time itself may have sparked into being then. Can you imagine such a thing? A true genesis, the spectacular singular birth of everything we know and everything we don't yet know, the ultimate beginning. This remarkable beginning was not slow or gentle. It was not gradual in the way we often see change. The absolutely crucial events happened incredibly fast. So fast, it is almost beyond comprehension. We are talking about the tiniest fractions of a second, smaller than any duration we can truly grasp, a fleeting, infinitesimal moment in time. Yet, this moment was all defining for the future. This is precisely where our incredible story starts, the very dawn of time itself. So, what was the universe like back then? During that very first primordial moment, it is incredibly hard for us to even imagine. The conditions were utterly extreme, beyond compare, far beyond all direct human experience or observation. Nothing familiar to us existed in that state. There were no stars, no planets, no atoms formed, just pure, undiluted, raw cosmic potential, awaiting the spark of transformation, a universe waiting to be born. The entire universe was unbelievably small then, perhaps smaller than a single proton, a tiny particle. Yet it miraculously contained all the future energy, all the fundamental stuff for countless future galaxies, all of it packed into an infinitesimal, dense point. The sheer density was truly staggering to consider, the ambient temperature almost infinitely high, a seething, energetic cauldron of cosmic creation, the ultimate crucible, forging reality. From this, everything would emerge. What about our familiar laws of physics today? The rules that govern how things work now. They might not have fully applied back then. Gravity, light, matter itself, as we know them. These fundamental aspects behaved very differently. Or perhaps they were not distinct forces at all. Maybe they were unified in a way we now seek to grasp. A singular primordial state beyond our current theories. This represents a true, exciting scientific frontier. Pushing the boundaries of understanding, peering directly into this ancient formative era is tough. It is like trying to look through a dense cosmic firewall, but dedicated scientists are absolutely relentless in their pursuit. They utilize complex mathematics and bold new theories. They meticulously search for the faintest, tiniest clues, possible remnants left over from that ancient fiery time. The genuine thrill is found in exploring the unknown. It is about unlocking the universe's deepest, oldest secrets. A challenge that inspires continued exploration. The quest for ultimate cosmic knowledge. Why does any of this ancient history matter to us? This complex tale of the very early universe. It might seem incredibly distant, very abstract, perhaps like purely theoretical physics with little connection. But it is profoundly more than just that. It is, in fact, our ultimate shared origin story. It is the fundamental story of how we all came to be. Our beginnings are deeply embedded in that fabric, the fabric of space-time born in that instant. We are children of this cosmic dawn. Those first incredibly fleeting, powerful moments, they effectively set the cosmic stage for everything. They determined the entire universe's ultimate fate, how it would dramatically expand and gradually cool, how vast cosmic structures would eventually begin to form, from the largest, most sprawling galaxy clusters imaginable, to the individual stars, their planets, and potentially life. Our very existence is inextricably tied to that start, a chain of events leading to us. Everything is connected to that origin. In this truly incredible, universe-defining opening act, two particularly key and fascinating phases take center stage. First, there is the mysterious Planck Epoch, a fleeting time of ultimate unity and profound mystery. This was immediately followed by cosmic inflation, a mind-boggling period of astonishingly rapid expansion. These two critical phases are our primary focus. They represent the universe's truly wild, formative beginnings, where the cosmos took its initial crucial shape, unveiling the blueprint of existence. So, please join us on this captivating journey. We will venture forth and explore these concepts, delving deep into what modern science currently suspects, and also acknowledging what still remains a profound puzzle. We will aim to see how the universe smoothed itself out, how unimaginably tiny seeds grew into vast galaxies. Prepare yourself for some truly mind-bending ideas. The universe's most ancient, compelling story awaits us, a story of fire, expansion, and creation. Let's begin this exploration together. We journey back to the very beginning, to the Planck Epoch. This unimaginably brief moment, called Planck time, lasted just 10 to the minus 43 seconds. The universe was smaller than an atom, hotter than any star, and filled with pure energy. All the laws of physics were unified, and everything we know began here. Understanding this instant is key to understanding the universe itself. Imagine a time when the universe was ruled by a single, unified force. Today, we know four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But in the Planck epoch, these were one. As the universe expanded and cooled, this unity shattered, giving rise to the forces we see now. Physicists still search for this lost unity, a true theory of everything. Our best theories, general relativity and the Standard Model, describe gravity and the quantum world beautifully, but at the Planck epoch, they break down and clash. Scientists seek a theory of quantum gravity to unite them. String theory is a leading idea, suggesting reality is made of tiny vibrating strings. The quest for these ultimate laws pushes human ingenuity to its limits. The Standard Model is our best theory of fundamental particles and forces, explaining nearly everything we see except gravity, dark matter, and dark energy. But at the universe's birth, its equations break down. The early universe pushes us to seek a deeper theory, one that unites all forces and explains the cosmos at its most extreme. The quest for what lies beyond is just beginning. Gravity remains the biggest missing piece in our understanding of the universe. Einstein's general relativity describes gravity as the curvature of space-time, working beautifully for large-scale objects. Quantum mechanics, meanwhile, governs the tiny world of particles, using quanta to describe forces. The challenge: unify these two into a theory of quantum gravity. Such a theory would reveal what happens to space-time at the smallest scales, possibly a foamy, turbulent realm. It could explain singularities like black holes and the Big Bang, and unify all forces under one framework. But merging these theories is incredibly tough. The math breaks down, signaling missing ingredients. Cracking quantum gravity would revolutionize our understanding of the universe's origins. String theory is a leading candidate for quantum gravity. It proposes that fundamental particles are tiny, vibrating strings, not points. Different vibrations create different particles and forces, including gravity. String theory could unify all forces, but it requires extra hidden dimensions and predicts a vast landscape of possible universes. Direct evidence is elusive. Energies needed are far beyond current technology. Supersymmetry, another idea, suggests every particle has a heavier partner, potentially solving Standard Model puzzles. Grand unified theories aim to merge the strong, weak, and electromagnetic forces at high energies. The search for new physics is bold, mathematical, and ongoing. The Planck epoch was a fleeting moment of unimaginable conditions. As the universe expanded and cooled, gravity separated from the other forces. Soon after, the strong force split from the electro-weak force, ushering in the grand unification epoch. Then, around 10 CE, 36 seconds after the Big Bang, cosmic inflation began. The universe expanded exponentially, faster than light. Not objects moving, but space itself stretching. This rapid growth was powered by a mysterious energy field, the inflaton. The inflaton's energy acted like anti-gravity, driving the universe's most dramatic growth spurt. Inflation set the stage for everything that followed. Before inflation, cosmologists faced big puzzles. The horizon problem. Why is the cosmic microwave background so uniform, even in regions that couldn't have interacted? Inflation solves this by stretching a tiny, uniform region to cosmic scales, allowing everything to reach the same temperature. The flatness problem. Why is the universe's geometry so flat? Inflation's immense expansion smoothed out any initial curvature, making the universe appear flat, like inflating a wrinkled balloon. These solutions made inflation a powerful addition to cosmology. It explained the universe's large-scale uniformity and geometry. Inflation's answers reshaped our understanding of the early cosmos. The inflaton field powered inflation. It was a scalar field with high potential energy trapped in a false vacuum state. This energy drove exponential expansion, acting like anti-gravity. Eventually, the inflaton rolled to its true minimum, ending inflation. Its energy was released in a process called reheating, filling the universe with hot, dense particles. This marked the start of the hot Big Bang era. The universe was now primed for the formation of matter, atoms, and galaxies. Inflation's end set the stage for cosmic evolution. Even after inflation, the universe wasn't perfectly smooth. Quantum mechanics ensures constant, tiny fluctuations in energy. Quantum fluctuations. These are a fundamental feature of reality, not measurement errors. During inflation, these fluctuations were everywhere, like tiny ripples on a calm ocean. They were variations in the energy density of space itself. These minuscule differences became the seeds of future complexity. Without them, the universe would be too uniform for stars or galaxies to form. Quantum fluctuations were crucial for cosmic structure. Inflation magnified quantum fluctuations to cosmic scales. Tiny subatomic ripples became vast undulations across the universe. This process bridged the quantum world and the cosmos. Imagine a small pattern on a balloon stretched huge as it inflates. So too with quantum fluctuations. These energy variations became blueprints for cosmic structure. Some regions had slightly more energy, others less. Tiny differences with big consequences. These were the primordial seeds for galaxies and cosmic voids. Inflation amplified quantum whispers into the universe's grand design. After inflation ended, the universe underwent reheating. The energy of the inflaton field converted into particles, creating a hot, dense soup of matter and radiation. This matter was not distributed perfectly evenly. It inherited the slight density variations that inflation had stretched from quantum fluctuations. Some regions of space now had slightly more matter, while other regions had slightly less matter due to those seeds. These were the very beginnings of cosmic structure, the subtle density landscape forged by inflation. These slightly denser regions possessed slightly more gravity. Gravity, as we know, is the great cosmic architect. Over vast stretches of cosmic time, gravity went to work. The regions with a little extra mass began to pull, attracting more matter from their surroundings. Slowly, inexorably, these denser areas grew even denser, while the less dense regions became emptier. This process is known as gravitational collapse, and it is the fundamental mechanism for structure formation. The tiny initial seeds started to grow. Over millions and then billions of years, this continued. The matter clumped together more and more. The first stars ignited within these collapsing clouds of gas, and these stars then grouped together to form the very first galaxies. Galaxies in turn were drawn together by gravity, forming larger structures called galaxy clusters and superclusters. The less dense regions evolved into vast cosmic voids, creating the sponge-like, web-like pattern of the universe, the large-scale structure we observe today through our telescopes. All of this originated from those tiny quantum fluctuations. It is, honestly, a truly mind-boggling connection to comprehend. The largest structures in the entire observable universe, the immense filaments and walls of the cosmic web, they owe their existence to the inherent uncertainties of the quantum world, active during inflation's first moments. Those fleeting, microscopic energy ripples were the cause, stretched by inflation, then sculpted by gravity over eons. They became the galaxies, stars, and ultimately us. We are, in a very real sense, the cosmic descendants of quantum fluctuations from the dawn of time. Cosmic inflation may never have ended everywhere at once. In some regions, the inflaton field kept expanding space, creating new universes, bubbles in a vast cosmic ocean. This is eternal inflation, a process where new universes constantly form, each with its own story. Our universe is just one bubble among countless others, forever expanding in a cosmic multiverse. Eternal inflation may create countless universes, each a bubble with its own unique laws of physics. Some might have stronger gravity, different particles, or even more dimensions. Most would be inhospitable to life, but in a vast multiverse, it's not surprising that at least one, like ours, has the right conditions. We find ourselves in a hospitable bubble because we couldn't exist anywhere else. The idea of a multiverse is staggering. If true, our universe is just a single grain of sand on an infinite cosmic beach. This humbling thought challenges our sense of uniqueness and compels us to expand our perspective. Whether or not we ever prove the multiverse exists, it forces us to reflect on our place in the cosmos. The universe, or multiverse, is more magnificent than we ever imagined. Our quest for understanding continues. We have journeyed to the universe's earliest, most extreme moments, exploring the Planck epoch and the mind-bending surge of cosmic inflation. Modern science offers breathtaking glimpses into this primal dawn, yet so much remains shrouded in mystery. Our quest to understand these beginnings is more than academic. It's a fundamental human desire to find our place in the cosmos. Each discovery adds a thread to this grand tapestry. Imagine a moment so early, our usual measures of time barely apply. The universe had just finished an astonishing growth spurt, cosmic inflation, expanding from smaller than an atom to larger than a galaxy in a fraction of a second. Now, the universe was vast, filled with raw, chaotic energy. The frantic pace slowed, setting the stage for everything to come. The true beginning had arrived. The cosmic drama was about to unfold. The post-inflationary universe was a sea of unimaginable energy, pure, undifferentiated power, hotter than anything we can imagine. No atoms, no particles, just a turbulent ocean of potential. In this crucible, the fundamental forces were unified, waiting to separate and shape the cosmos. From this energy, the first quarks, electrons, and eventually stars and planets would emerge. The universe's story began here, in a furnace of creation. The universe began as a vast expanse of pure energy, brimming with potential. From this primordial state, the first particles formed, guided by the fundamental forces. Gravity shaped the cosmos, while other forces split and took on their unique roles. Atoms gathered, stars and galaxies emerged, and eventually life arose on a small planet. Our existence is an unbroken chain, stretching back to this cosmic dawn. The universe, fresh from its inflationary sprint, was now a vast, seething cauldron of pure energy. Temperatures were beyond imagination, yet cooling from the chaos of inflation. In this energetic furnace, energy began transforming into mass. Einstein's E equals mAc squared in action. For a fleeting moment, conditions were just right for the first, most fundamental particles to emerge. These pioneers marked the dawn of tangible reality, tiny whispers of order in a chaotic universe. As the universe cooled, the first elementary particles to emerge were quarks, fundamental building blocks of matter. There are 6 types, with names like up, down, charm, strange, top, and bottom. In the earliest moments, up and down, quarks dominated, zipping through a dense, energetic quark-gluon plasma. Gluons, the carriers of the strong force, acted as cosmic glue, binding quarks together. As the universe cooled further, most quarks vanished, but a tiny residue survived, seeding all future matter. As the universe cooled, a new family of particles emerged, leptons. Among them, electrons, negatively charged, vital for atoms, appeared, zipping freely through the hot plasma. Alongside, ghostly neutrinos formed, nearly massless, chargeless, and barely interacting with anything. Billions of neutrinos streamed through space, silent witnesses to the universe's birth. With quarks, electrons, and neutrinos now present, the universe's particle zoo was growing richer and more complex. These fundamental particles set the stage for everything to come. With quarks, electrons, and neutrinos in play, cosmic time gained meaning. Events could now be marked. The universe, once a blur of energy, became a sequence of particle births and interactions. Each new particle species was a tick of the cosmic clock, driven by relentless expansion and cooling. The universe was a dense, hot fog of particles. No atoms yet, no free light, just chaos and potential. These first fractions of a second set the initial conditions for everything that followed. The stage was set for the next act, the formation of atomic nuclei. As energy became matter, nature demanded symmetry. Every particle had an antiparticle twin. Electrons came with positrons, quarks with antiquarks. For every bit of matter, an equal bit of antimatter. The universe was a balanced mix, a perfect mirror of particles and antiparticles. But when matter met antimatter, they annihilated in a flash of energy. This cosmic symmetry set the stage for a dramatic confrontation. The universe was primed for a battle between something and its opposite. In the universe's first second, matter and antimatter collided everywhere, annihilating in bursts of light. Nearly all particles and antiparticles vanished, their mass converted to photons. The universe was a fireworks show of creation and destruction. If matter and antimatter had been perfectly balanced, nothing but light would remain. No atoms, no stars, no life. But a tiny imbalance changed everything. The great annihilation cleared the way for what would come next. Only a sliver of matter survived. We exist because the universe wasn't perfectly symmetrical. For every billion antiparticles, there was one extra particle of matter. This tiny surplus, 1 in a billion, became the seed of everything: galaxies, stars, planets, us. The reason for this imbalance, called baryogenesis, remains a mystery at the frontier of physics. Without it, the universe would be empty, filled only with light. Our existence is a testament to this ancient imperfection. The universe's slight preference for matter made all the difference. After the annihilation, a universe flooded with photons remained, but so did a precious few survivors, quarks and electrons. These 1 in a billion particles were the building blocks of everything to come. Now, with most antimatter gone, matter could begin to assemble. The universe was still a hot plasma, but the drama of creation and destruction had ended. The survivors would soon combine, taking the first steps toward atoms. The material universe had truly begun. The annihilation left behind a legacy, a vast sea of photons, the universe's first light. This photon bath filled space, keeping the universe hot and opaque. Atoms couldn't form yet. Any attempt was undone by high-energy photons. Matter floated in this intense ocean of light, suspended and waiting. As the universe expanded, the photon energy slowly dropped. Only when it cooled enough could atoms finally form and the universe become transparent. For now, the cosmos simmered in its own radiance. Barely a microsecond after the beginning, the universe cooled enough for quarks to be trapped together. The strong force-bound quarks into hadrons, protons and neutrons, the building blocks of atomic nuclei. Free quarks vanished, replaced by these new, more complex particles. The universe shifted from a quark-gluon plasma to a dense gas of protons, neutrons, electrons, neutrinos, and photons. This transformation happened swiftly, setting the stage for the next cosmic leap. The first atomic nuclei were about to form. All of this unfolded within the universe's first second. So, quarks were now confined. They formed particles called protons and neutrons. A proton consists of 2 up quarks and 1 down quark, and it carries a positive electric charge. A neutron contains 1 up quark and 2 down quarks, and it has no electric charge. It is neutral. These particles are the core components of atomic nuclei, and their emergence was a pivotal moment. The universe was building its essential Lego bricks, if you will. These newly minted protons and neutrons were not static, though. They existed in a hot, dense, dynamic environment. The universe was still just a fraction of a second old. Protons and neutrons could actually change into one another. A neutron could decay into a proton, an electron, and an anti-neutrino. On the other hand, a proton could combine with an electron to become a neutron and a neutrino. These transformations were pretty common in the extreme heat. A delicate balance determined their relative numbers. More protons than neutrons, but only by a small margin. This slight imbalance between protons and neutrons was actually crucial. Neutrons are just a bit more massive than protons, and this tiny mass difference plays a significant role. It meant that as the universe cooled, it became energetically favorable for neutrons to convert to protons. If neutrons had been lighter or protons unstable, the universe might have ended up very different, perhaps with no hydrogen to fuel stars for billions of years. The laws of physics were sculpting the cosmic ingredients. The universe was now a seething soup: protons, neutrons, electrons, neutrinos, and photons, all packed together at incredible densities. The temperature was still far too high for atoms to form. Electrons could not yet bind to protons or neutrons. Any such attempt would be instantly thwarted, as a high-energy photon would knock the electron away. The cosmos was a roiling, opaque plasma, but the first steps towards nuclear fusion were near. Protons and neutrons now populated the universe. They were the raw ingredients for atomic nuclei. The strong nuclear force wanted to bind them together. A proton and a neutron could stick together, and this would form a nucleus called deuterium. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron. It's the very first, simplest compound nucleus, a crucial stepping stone to heavier elements. But yeah, there was a problem, a cosmic bottleneck. The universe was still incredibly hot, full of highly energetic photons. These photons were particles of light, but with immense power. If a proton and neutron managed to combine, forming a fragile deuterium nucleus, it was immediately blasted apart. A high-energy photon would strike it, breaking the bond and separating them once more. This is known as the deuterium bottleneck. So, for a short but critical period, no significant nucleosynthesis could occur. Protons remained largely as individual protons, or hydrogen nuclei, and neutrons remained mostly as individual neutrons. The universe had to cool down further. The average energy of the photons needed to decrease. Only then could deuterium nuclei survive. Only then could they last long enough to participate in further nuclear reactions. This delay was actually essential for the future composition of the universe. If fusion had started too early, when neutrons were more abundant, perhaps much more of the hydrogen would have become helium. The universe needed to wait. About 1 second after the Big Bang, the temperature finally dropped sufficiently to around 10 billion degrees Celsius. Deuterium nuclei could now hold together. The bottleneck was about to break. The cosmic waiting game was over. The universe reached the right temperature, and deuterium nuclei could now survive the photon bath. Protons and neutrons began to fuse successfully. This marked the beginning of Big Bang nucleosynthesis, the very first nuclear fusion in the history of the cosmos. It all started around 1 second after the Big Bang. A pivotal moment had arrived. The universe was becoming a nuclear furnace. Once stable deuterium formed, the floodgates opened. Deuterium nuclei quickly captured more particles. A deuterium nucleus could fuse with another neutron, forming tritium, which is an isotope of hydrogen with 2 neutrons. Or deuterium could fuse with a proton, creating helium-3, an isotope of helium with 2 protons and 1 neutron. These reactions happened rapidly. The early universe was a busy nuclear reactor, building up the first light elements. The primary product of this cosmic fusion was helium-4. Helium-4 has 2 protons and 2 neutrons, and it is an exceptionally stable nucleus. Most of the available neutrons were quickly incorporated. They combined with protons to form helium-4. Some tritium and helium-3 also fused, creating more helium-4. The process was remarkably efficient, and a significant fraction of matter became helium. This intense period of element creation lasted only a few minutes, from about 1 second to roughly 3 minutes. After 3 minutes, the universe had expanded and cooled further. Temperatures and densities dropped too low for sustained nuclear fusion to continue. The nuclear furnace of the Big Bang shut down. It had done its job swiftly, leaving behind a specific mixture of elements. The primordial chemical composition of our universe was set. So, after about 3 minutes, nucleosynthesis wound down. What was the universe made of now? Primarily, it was a hot, dense plasma, a soup of atomic nuclei and free electrons. The dominant element was hydrogen, making up about 75% of the ordinary matter by mass. These were mostly single protons, hydrogen nuclei. The next most abundant element was helium-4, making up almost all of the remaining 25%. Tiny traces of other light elements were also forged. A very small amount of deuterium survived. Some helium-3 also remained, and even smaller quantities of lithium-7 were produced. Elements heavier than lithium were not made, not in any significant amounts during Big Bang nucleosynthesis. The conditions were no longer right. The universe expanded and cooled too quickly. The first stars would later create heavier elements. This hot plasma was still opaque to light. Photons could not travel far. They constantly bumped into the free electrons, scattering in all directions, absorbed and re-emitted. Imagine being inside a tremendously dense fog, but a fog that was blindingly bright and hot. This was the state of the entire universe. No stars, no galaxies, just this uniform, glowing plasma. A cosmic soup simmering for thousands of years. The universe had taken crucial steps, from pure energy to fundamental particles, from quarks to protons and neutrons, and now to the first atomic nuclei, hydrogen and helium, the fuel for future stars. The universe was filled with the raw materials for galaxies. It was now a relatively stable, though still evolving, place. The stage was set for the next great transition, the slow cooling that would eventually allow atoms to form and for light to finally travel freely across the cosmos. In the universe's first minutes, chaos gave way to a new order. Hydrogen and helium nuclei formed in a searing plasma, with free electrons darting among them. The cosmos was a vast glowing ocean, hotter than the sun's core, filled with energetic particles and intense light. Though stable, it was far too hot for atoms to form. The universe waited, still sizzling, for its next great transformation. After nucleosynthesis, the early universe was a hot, brilliant plasma. No stars, just a dense fog of light and free electrons. Photons collided constantly with electrons, trapping light and making the universe completely opaque. It was like a cosmic pinball machine. Light bouncing endlessly. No clear view, just a uniform, blinding haze everywhere. Only as the universe expanded and cooled did this luminous fog finally begin to clear. In the early universe, intense heat and energetic photons kept atoms from forming. Electrons and nuclei tried to combine, but photons would instantly break them apart. The electromagnetic force pulled particles together, while light tore them apart, a cosmic tug-of-war. Only as the universe cooled could atoms finally form, marking a pivotal moment in cosmic history. The universe, a searing plasma of nuclei and electrons bathed in energetic light, couldn't stay this hot forever. The key to its future transformation lay in a process that had been ongoing since the very first moment: expansion. The fabric of space itself was stretching, carrying galaxies and clusters of galaxies away from each other over cosmic eons. In these early times, this expansion was the primary engine of change. As the universe expanded, the energy within it became more spread out, more dilute. This dilution effect was critical for cooling the pervasive bath of photons that kept atoms from forming. How does expansion cool light? It's a fascinating consequence of cosmic physics known as cosmological redshift. As a photon travels through expanding space, its wavelength gets stretched. Think of a wave drawn on a rubber sheet, and then you stretch the sheet. The wave gets longer. For light, a longer wavelength means lower energy. So, as the universe expanded, the incredibly energetic photons from the early hot phases gradually lost their punch. Their wavelengths were stretched, shifting them from high-energy gamma rays and X-rays towards lower-energy ultraviolet and, eventually, visible light. This was not a fast process. It was a slow, relentless diminishment of energy over vast timescales. The period of nucleosynthesis, where hydrogen and helium were forged, lasted only a matter of minutes, but the cooling period required for atoms to finally form would stretch on for hundreds of thousands of years. It was a long, patient waiting game. The universe, having established its basic particle content and its initial elemental composition, now entered a prolonged phase of simply expanding and cooling, slowly paving the way for the next great leap in complexity. This was a simmering down, a gradual release of the primordial heat. The universe was patiently biding its time, its state dictated by this slow temperature drop. Every moment of expansion brought it closer to the critical threshold where the average energy of photons would dip below the binding energy of electrons in atoms. This wasn't an active process of doing something new, but rather a passive evolution driven by the fundamental nature of an expanding cosmos. The stage was being meticulously set for recombination, the epoch when electrons would finally combine with nuclei to form stable, neutral atoms. This great cosmic cooldown was the necessary prelude to the universe becoming transparent and allowing the first light to travel freely, a story for another chapter. While the early universe after nucleosynthesis was remarkably uniform, a hot, dense, opaque plasma filling all of space, it wasn't perfectly smooth. Hidden within this seemingly featureless fog were incredibly subtle variations in density, tiny ripples in the otherwise homogeneous distribution of matter and energy. These were not dramatic mountains and valleys, but differences so minuscule they would be almost imperceptible. Yet these slight imperfections, these almost infinitesimal fluctuations, held the key to the entire future structure of the cosmos. They were the primordial seeds from which all galaxies, stars, and planets would eventually grow. Where did these crucial imperfections come from? They are believed to be the echoes of the universe's very earliest moments, originating as tiny quantum fluctuations during the period of cosmic inflation. Inflation, that incredible burst of hyper-expansion, took these microscopic quantum jitters and stretched them to enormous astrophysical scales. So, by the time the universe was a hot plasma, these quantum whispers had become gentle, large-scale variations in density. Some regions were ever so slightly denser than average, while others were slightly less dense. These were the initial blueprints for cosmic structure, imprinted onto the fabric of space-time itself. Dark matter, that mysterious invisible substance that interacts primarily through gravity, played a crucial role here. Because dark matter does not interact with light or photons or with the electromagnetic force, it was not buffeted about by the energetic photons in the plasma like ordinary matter. Protons, neutrons, and electrons was. In those slightly denser regions, dark matter could begin to clump together, its gravitational pull slowly but surely accumulating more dark matter. It began to form halos, invisible gravitational wells that would later attract ordinary matter. The ordinary matter, still locked in the hot plasma, couldn't collapse yet, but the dark matter was already laying the gravitational groundwork. These subtle density fluctuations, amplified by the gravitational influence of dark matter, were the first hints of emergent structure. While the universe was still an opaque, glowing fog, these invisible seeds of future galaxies were quietly developing. The uniform plasma was not destined to remain uniform forever. Gravity, acting on these initial variations, would eventually draw matter together, forming the vast cosmic web of galaxy clusters, filaments, and voids that we observe today. The universe, even in its seemingly homogeneous youth, was already pregnant with the potential for the rich, complex tapestry of structures that would later fill the night sky. The stage was being set for gravity to sculpt the cosmos. For hundreds of thousands of years, the universe expanded and cooled. The searing heat faded and a profound change approached. Around 380,000 years after the Big Bang, the universe reached a tipping point. Protons began to capture electrons, forming the first neutral atoms. The universe shifted from a charged plasma to a calm sea of atoms. The dawn of atoms had arrived, changing the universe forever. Before atoms, the universe was a glowing fog of charged particles. Photons, the particles of light, were trapped, constantly scattering off free electrons. But as electrons joined nuclei to form neutral atoms, the fog lifted. Suddenly, light could travel freely across space. The universe became transparent, revealing the cosmos and carrying the first light across billions of light years. The light released at recombination is the oldest we can see, the cosmic microwave background, or CMB. These ancient photons have traveled over 13 billion years, carrying a snapshot of the universe as it became transparent. The CMB is a faint, uniform glow from every direction, the afterglow of the Big Bang, and its tiny fluctuations reveal the seeds of all future galaxies. And so, the universe stepped out of its opaque infancy. Light, once trapped within a fiery, dense plasma, was finally free. This happened around 380,000 years after the Big Bang, a moment we call recombination, when atoms first formed. The photons from that era, suddenly liberated, began an immense journey. They streamed across the cosmos, carrying a message from a time when the universe was incredibly young. This ancient light, the cosmic microwave background, is that message. It is the oldest light we can ever hope to see, a relic of creation, a whisper from the dawn of transparency, now reaching our telescopes. This cosmic microwave background, or CMB, is truly remarkable. It is the afterglow of the universe's fiery birth. Imagine the entire sky glowing, faintly but persistently, not with the light of individual stars, but with this primordial radiance. It comes to us from every direction with astonishing uniformity, a near-perfect echo of a much hotter, denser state. This light has traveled for over 13 billion years to reach us, its wavelength stretched by the expansion of the universe itself. From brilliant visible and infrared light, it has cooled. Now it arrives as microwaves, a gentle hum from the distant past. The CMB is more than just old light. It's a photograph. It's the universe's very own baby picture. It shows us what the cosmos looked like at that tender age, a time before any stars or galaxies had yet ignited. This picture reveals incredibly subtle temperature variations, tiny ripples, just 1 part in 100,000. These are not flaws. They are the seeds of everything, the slight differences in density that gravity would later amplify, turning a nearly uniform soup into the rich tapestry of galaxies. These faint patterns hold the blueprint of cosmic structure. Studying this faint glow allows us to test our understanding, our theories about the Big Bang and the early universe. The CMB provides powerful evidence supporting this cosmic story. Its existence, its temperature, its tiny fluctuations, all match predictions. It tells us about the age of the universe, its composition. It even hints at the physics of the inflationary period. This echo of the dawn is a cosmic treasure trove, allowing us to piece together the grand narrative of our origins, from an almost featureless glow to the complex cosmos we inhabit today. The universe's first light continues to illuminate its deepest secrets. The release of the cosmic microwave background marked the end of the universe's opaque era and the beginning of something profound. The universe became transparent, filled with hydrogen and helium, waiting for gravity to gather atoms. Dark matter provided the scaffolding as ordinary matter slowly fell in. Over millions of years, gas clouds grew denser and hotter, preparing for the first stars. The birth of light at recombination was just the dawn. The cosmos began with the Big Bang, an explosion of unimaginable energy. In its first moments, the universe was a hot, dense plasma where light couldn't escape. As it expanded and cooled, protons and electrons combined to form hydrogen and helium atoms. The universe became transparent, but with no stars or galaxies, darkness prevailed. This was the cosmic dark ages, a silent, empty expanse, waiting for the first light. Only faint whispers of the Big Bang's afterglow lingered in the cold, growing void. The darkness held promise, hydrogen and helium atoms drifting in the void, the seeds of everything to come. Gravity began its slow work, pulling matter together where tiny density ripples existed. Over millions of years, these regions drew in more gas, forming the first clouds. The universe was quietly preparing for a transformation, the birth of stars. The end of darkness would mark the dawn of complexity and light. As the universe expanded, its initial light stretched and faded, cooling the cosmos to just above absolute zero. The afterglow of the Big Bang became the faint cosmic microwave background. No stars or galaxies yet existed, only a cold, dark sea of hydrogen and helium. The universe was visually silent, waiting for new sources of light. This was the true cosmic dark ages, a time of patient stillness. The stage was set for the next chapter, creation from darkness. The universe was now a vast, transparent ocean of neutral hydrogen. No stars illuminated the darkness. Only gravity worked in silence. Tiny density variations began to gather gas, forming the first hints of structure. The darkness was not empty. It was a necessary prelude, quietly shaping the future. Gravity's patient hand was forging the conditions for the first stars. The universe waited, poised for its first spark of light. Gravity, relentless and subtle, sculpted the universe's fate. In denser regions, gas clouds slowly coalesced, guided by invisible dark matter halos. Over millions of years, these clouds grew massive, their gravity overpowering the urge to disperse. As they contracted, temperatures rose deep within their cores. The universe remained dark, but these clouds were islands of change. The first stars were about to ignite, ending the long cosmic night. In the densest cloud cores, temperatures soared to 10 million degrees. Hydrogen nuclei fused, unleashing the first starlight. Population 3 stars, massive and brilliant. These giants, hundreds of times the sun's mass, burned hot and bright, illuminating the darkness. Their intense radiation began to ionize the surrounding hydrogen, carving out bubbles of light. The cosmic dark ages ended locally as these stars transformed their environment. The universe's first stars were not just beacons, they were engines of cosmic change. It is highly probable that these first massive stars did not ignite in splendid isolation. The vast molecular clouds that collapsed to form them were turbulent places. The physical conditions that allowed one such giant star to form within a collapsing cloud often meant that many could take shape in the same general cosmic neighborhood, or in nearby smaller collapsing clumps of gas. These initial stellar nurseries likely gave birth to clusters containing dozens or even hundreds of these brilliant massive population 3 stars. These groups, gravitationally bound together, represented the first small coherent stellar systems, the earliest communities of fiery celestial bodies. The combined gravitational influence of such a cluster of first stars, significantly amplified by the dark matter halo in which they were embedded, was substantial. This collective gravity acted as a powerful cosmic magnet. It began to pull in yet more pristine hydrogen and helium gas from the surrounding intergalactic medium, the tenuous gas that filled the spaces between these nascent structures. Furthermore, it could also draw in and merge with other smaller clouds that were themselves on the verge of collapse, or even capture other fledgling clusters of stars. This ongoing process of accretion and merging was a fundamental mechanism for building up larger and more complex structures over cosmic time. These accumulating collections of population 3 stars and the gas they were gathering are what astronomers refer to as proto-galaxies. They were the direct precursors to the grand galaxies that populate the universe we observe today. However, these initial structures were vastly different. They were not the majestic, well-ordered spiral galaxies like our Milky Way, nor were they giant elliptical galaxies. Instead, these proto-galaxies were likely small, clumpy, and highly irregular in their appearance. They might have contained only a few million stars at most, a mere fraction of the hundreds of billions that reside in a mature galaxy like our own. Despite their relatively modest beginnings, these proto-galaxies were of paramount importance in the evolving universe. They were the crucibles where the chemical enrichment of the cosmos truly commenced, as these first massive stars rapidly burned through their fuel and ended their lives in spectacular supernova explosions, scattering newly forged heavier elements into space. Crucially, these proto-galaxies were the primary sources of the intense ionizing radiation that would eventually sweep across the entire universe. This radiation eventually lifted the pervasive veil of the cosmic dark ages everywhere, ushering in an epoch known as reionization. These small islands of light were the true dawn. The first stars burst into existence. Light, a new kind of light. It pierced the ancient cosmic darkness. This was not the Big Bang's faint echo. This light was fresh, born in fire. From the hearts of colossal stars, they burned with astonishing blue-white intensity. The universe was waking from its long sleep. This starlight was incredibly powerful. Ultraviolet radiation streamed outwards. It struck the cold, neutral hydrogen gas. This gas had filled the dark universe. Electrons were torn from their atoms. The hydrogen glowed, ionized once more. Bubbles of transparency began to expand. These were the first beacons in the night. The new light was an agent of change. It did more than just illuminate. It heated and transformed the gas. This influenced future star formation. Conditions inside these bright bubbles shifted. The universe was no longer static. Light and matter entered a new dance. the cosmos began to reshape itself. The universe lit up gradually. It was not a sudden, single event. Ionized bubbles grew around the first stars. They expanded, pushing back the dark. As more stars formed, bubbles merged, like individual lamps slowly lighting a vast room. This was the true cosmic dawn, a slow, beautiful emergence into light. These first stars were magnificent, but their lives were incredibly short. Being so massive, they burned fuel fast, hundreds of times the sun's mass. Their hydrogen ran out in mere millions of years. Our sun will burn for billions. Gravity then crushed their dying cores. A spectacular violent end was inevitable. This collapse triggered massive supernova explosions. The stars blasted their outer layers into space. Inside these explosions, magic happened. New elements were forged in the fire. Carbon, oxygen, iron, silicon, elements heavier than hydrogen and helium. For the very first time, they existed. These are the building blocks of our world. The supernovae scattered these new elements. They flew outwards, seed in the cosmos. Primordial gas clouds were enriched. Space was no longer just hydrogen and helium. It now held the ingredients for complexity, a fundamental change in cosmic chemistry. The universe was becoming more interesting. The raw materials for future worlds appeared. This chemical enrichment was vital. It allowed new kinds of stars to form. Population 2 stars, born from this enriched gas. They could be smaller, live longer. Heavier elements also formed dust. Dust helped gas clouds cool and collapse. This led to smaller stars and planets. The stage was set for complex chemistry and, perhaps, life. As the first stars and proto-galaxies began to flicker into existence, they were not forming in a completely empty void. The universe, we now understand, possesses a vast unseen architecture. This hidden framework is made of something truly mysterious. It is a substance known as dark matter. It vastly outweighs all the ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and gas clouds. This realization has profoundly reshaped our understanding of cosmic evolution. Dark matter does not interact with light, rendering it invisible to our telescopes, yet its gravitational influence is immense, shaping the destiny of everything that shines. Dark matter began its work long before the first stars ignited. In the very early universe, while ordinary matter was still buffeted by intense radiation, dark matter particles were largely immune. They felt only the pull of gravity. Because of this unique property, dark matter began to clump together much earlier than ordinary matter. It formed vast, diffuse halos. Invisible concentrations of mass spread throughout the cosmos. These halos acted as gravitational wells, like gentle depressions in the fabric of space-time. They became the gravitational seeds around which visible structures would later form, the unseen foundations for the luminous universe. The primordial hydrogen and helium gas, cooling after the Big Bang, naturally felt the gravitational attraction of these pre-existing dark matter halos. The gas began to flow towards these concentrations, drawn into their deepening gravitational embrace. It was within these dark matter halos that the conditions for the collapse of gas clouds and the birth of the first stars became most favorable. Without dark matter's early gravitational work, the formation of stars and galaxies would have been a much slower, perhaps even impossible process. Dark matter effectively provided the cosmic scaffolding, guiding the assembly of the first luminous structures in the universe, accelerating their emergence from the dark ages. The distribution of dark matter, therefore, dictated the large-scale structure of the early universe. It wasn't a random scattering. Instead, it began to form an intricate network of filaments, sheets, and voids, a cosmic web. The proto-galaxies and clusters of stars preferentially formed along these dense filaments of dark matter, like beads on an invisible string. The vast empty regions, or voids, were areas with less dark matter. Mapping the positions of the earliest galaxies thus gives us an indirect map of this underlying dark matter skeleton. Understanding this invisible framework is absolutely crucial for piecing together the complete story of how the universe evolved from a nearly uniform state to the richly structured cosmos we observe around us today. While dark matter pulled matter together, forming stars and galaxies, another force emerged: dark energy. Dark energy acts as a kind of anti-gravity, pushing space apart. Its discovery in the 1990s revealed the universe's expansion is accelerating. As matter thinned out, dark energy's influence grew, overtaking gravity on the largest scales. Now, galaxies recede from each other faster and faster. Understanding dark energy is one of cosmology's greatest mysteries, shaping the universe's ultimate fate. The universe is not just expanding, its expansion is accelerating. This astonishing discovery, driven by observations of distant supernova, revealed a mysterious force: dark energy. Dark energy acts against gravity, pushing galaxies apart at an ever-quickening pace. Over time, galaxies not bound to us will vanish beyond a cosmic horizon, their light lost forever. We live in a special era, able to witness the universe's vastness before it fades from view. What is the ultimate fate of our accelerating universe? The answer depends on the true nature of dark energy. If dark energy remains constant, the universe will expand forever, growing colder and emptier, a scenario known as the Big Freeze. Galaxies will drift apart, stars will die, and all activity will cease in a cold, silent cosmos. Or, if dark energy grows stronger, the universe could end in a dramatic Big Rip, tearing apart galaxies, stars, and even atoms. Some theories imagine endless cycles of rebirth, a cosmic renewal. The universe's true ending remains one of science's greatest mysteries. Our journey through the cosmos began in darkness, when the universe was silent and unlit. Gravity gathered hydrogen, igniting the first stars, cosmic forges that created the elements of life. Their light ended the cosmic night, and the universe awakened. Dark matter shaped galaxies, while dark energy drives expansion. From the first light to the ever-expanding universe, we are connected to this grand story. We gaze at the stars, seeking our origins and our cosmic future.